All right, so last week would have been all the way back to last Monday. We talked about radians. We just reviewed that homework with it, right? And remember, radians is just an alternate way of dividing up a circle to figure out the opening of an angle. And so instead of cutting a circle into 360 slices and getting a degree, we're going to instead relate the arc length to the radius. And so that's what should be in your mind when you think of a radian. It's the amount of opening when the arc length equals the radius. And about how many degrees is that? Anybody remember? About how many degrees is one radian? 57.296. If just take 180 divided by pi, that's one radian, right? If you convert a radian to degrees, you would multiply times 180 divided by pi. So just take 180 divided by pi, and you'll get 57.296, I think it is, degrees. All right, so, and we dealt with trig in a Cartesian plane the lesson before that, where we understood that instead of relating the sine with opposite over hypotenuse, in a Cartesian plane or coordinate plane, the opposite is actually the y-coordinate, and the hypotenuse is the radius. So instead of saying opposite over hypotenuse, we could say y over r, the opposite being the y-coordinate and the radius being r. And we did that for the sine, we did that for the cosine, x over r, and we did it for the tangent, y over x. Well, now we come to a unit circle, and a unit circle is important because when you look at the base trig functions, you can take your calculator, you can do it now if you want, take your calculator out, punch in any angle you want, hit your sine button, and just punch in, anything. Positive, negative, 1,000 degrees, 1,000,000 degrees, 748 degrees, 999 degrees, 22 degrees. And notice that your values never go higher than what and lower than what. I mean, no matter what you punch, you're not going to get a value higher than 1, and you're not going to get a value lower than -1. And all this ties into a unit circle. So that's the idea today is now let's put radians together with a unit circle. So A here is a unit circle. So it ties into trig in a Cartesian plane. The big difference is, and the only difference is, the radius is 1. It's a set radius. Unit circle. It's kind of like the base model. Unit circle. So we'll make the radius 1, and then we'll work off of that. So in a unit circle, the radius stays 1, and therefore then we don't have to worry about the radius. All right, so progression here as we're thinking through our trig functions. So again, what is the sine? Opposite over hypotenuse. But in a Cartesian plane, the opposite is the y. The hypotenuse is the r. And again, that's just opposite over hypotenuse. Let me go over here. Let's label the triangle here on our unit circle. So across from the angle would be y, right? Right across from the angle, this value is y, right? Whatever value is there. And this value here is x, right? And the y would correspond to the opposite, the x would correspond to the adjacent, and of course the 1 is the radius. So again, the sine is the opposite over the hypotenuse, so it's y over r, only in this situation, the r just happens to be 1. So bottom line, what is the sine? Is y. So if they ask you the sine of an angle, and they show you the coordinates of a point, and it's a unit circle, then it's just the y-coordinate. That's it. It's amazing how I'll give a question like this on a test, and students will take minutes and minutes trying to figure out the answer to the question, and it was simply the y-coordinate. That was it. There was no figuring to be done at all. The sine of the angle was simply the y-coordinate. Because the radius is 1, the hypotenuse is 1, and therefore it's just y. And so, same concept with the cosine. Cosine is the adjacent, in this case x, normally over the hypotenuse r. But again, what's r? It's 1. So you just get x over 1, which is x. So for unit circle, the sine of theta is y, the cosine of theta is x, and the tangent is the opposite, the y, over the adjacent, the x. And guess what? That just stays y over x. So you will notice whether it's a unit circle or any circle, the tangent's always y over x. Yes, ma'am? Okay, so tangent's going to stay because the tangent doesn't relate to the hypotenuse, the radius, and therefore it just stays. So the sine is y, the cosine is x, and the tangent is y over x. That's pretty simplistic. Not a whole lot there, but it is something you have to remember. All right, so, applying it. So here you've got the coordinates of a terminal point, 0.4226 and negative 0.9063. It's going to put it about there around the circle, right? If you do x and y coordinates, positive x and negative y is going to stick you about there. And so what is the sign? You're just going to write the y coordinate. That's it. Negative 0.9063. Right? It's just the y coordinate. That's all. And the cosine is just the x coordinate. And the tangent is just the dividing of the two. You're not going to leave your answer like that for the tangent, are you? Right, you're not going to leave it like that, are you? Because you realize that both of those are round-offs already, and therefore you're just going to divide it out and get one more round-off. And negative 2.1446. Anybody concur? Negative 2.1446. Okay, real simplistic if you understand the concept, but again, for some reason, by the time we get to a test, students will be doing all kinds of figuring, trying to figure out the situation. Or, here's what will get you. Instead of giving you the drawing, I'll say something like this. So find the sine, cosine, and tangent for a unit circle where the terminal point coordinates are, and then I'll tell you 0.4226 and negative 0.9063. So I won't give you the drawing. I'll instead just give it to you in words, and then you'll do all kinds of crazy stuff trying to figure it out. Okay? So I just took this question in visual form and just put it in written form. The terminal point is this point right here, right? Which then allows you to form a right triangle and allows you to do all that you're doing. Not a big deal. That should be pretty simplistic if you remember what to do. All right, next scenario. So here we are back now to finding exact values. What's the exact value of the cosine of 7 pi over 6? So again, you have to have some idea of the way the fractions go. If not, you're going to have to look at the references, but you're not going to have the reference on the test. So use the references as long as you need to until you begin to figure out what's going on. So again, I'm thinking, so I already understand that this is 1/6 and 2/6 and 3/6 and 4/6 and 5/6 and 6/6, and therefore then 7/6 is about like that. Seven pi over 6. Which means the reference angle is what? Pi over 6. Again, you may not understand that the reference angle is pi over 6 because you don't think very well in radians and you're fractionally challenged. Why, I don't know, but you are. So what else could you do? You could just simply convert the whole thing right off the bat. And maybe that's going to be best for a lot of you. You just change it to degrees and figure it out in degrees. And so, what is this, 210 degrees? But again, if you look at the reference, this is 1/6, 2/6, 3/6, 4/6, 5/6, 6, 6, 7, 6. It is good if you can get to the point where you can think both ways. It just makes life easier. All right, so bottom line, the reference angle is how many degrees? 30 degrees. All right, can you finish it from there? So you got a 30-degree reference angle. Find the exact value of the cosine of 7 pi over 6. Watch your positives and negatives. Careful with your positives and negatives. All right, cosine what? Adjacent over hypotenuse, and so square root of 3 over 2, negative square root of 3 over 2. How many got that? Okay, so again, what were you doing? Now you got your reference triangle. Okay, why did I stick this on the page? Because that's the pattern for a 30-degree or 60-degree angle. Now you just got to figure out which side is where. If you have trouble figuring out which side is where, use your angles. The side between the 90 and the 60 is the 1. In this case, the 1 is negative because you can clearly see that it's below, it's on the negative y-axis. What's the side between the 30 and the 90? The square root of 3. And again, you can clearly see it's negative because it's on the negative x-axis. What's the cosine? You can either think it's the x over the r, or you can think it's the adjacent over the hypotenuse. What's the adjacent? Negative square root of 3. What's the hypotenuse? 2. Any questions on that? Any questions on that? Okay, do the next one then. Go ahead and figure out the exact value of the sine of negative 5 pi over 4. The exact value of the sine of negative 5 pi over 4. All right, on 3, give me your answer. 1, 2, 3. Okay, so square root of 2 over 2. You know, on this one, you got to count backwards because it's negative. So this is negative 1/4, negative 2/4, negative 3/4, negative 4/4. So negative 5/4 is right here. Again, if you have trouble doing that, you can right off the bat just convert it to degrees. You think better in degrees than you think in radians. So what do you get out of this? 135 degrees, I guess? Well, negative 225 would be what you would get going that way. So that puts us right here, right? Is a 45. And now it's the exact same situation. You're going to use your pattern. You're going to fill out the signs of the triangle. In this case, this is a unit circle. Oh, I take that back. Radius is square root of 2. On both sides. This one's 1 and this is negative 1. Just be careful on the negatives. Right? Again, why is that negative 1? It's on the negative x-axis. Why is this one positive 1? Because it's off the positive y-axis. Right? And then you're just doing the sine is the opposite over the hypotenuse. So sine of negative 5 pi over 4 is the opposite 1 over the hypotenuse square root of 2. Just rationalize the denominator. And voila, you are done, right? So square root of 2 over 2. Okay. All right, on the bottom here, I did try to give you guys, again, a picture of the 45, 45, 90, 30, 60, 90. I want to do one more thing with you guys, and that's show you one other aspect. And this is number 4. And it's polar coordinates. Polar coordinates. This is for when you go to the North Pole or South Pole. You need polar coordinates. Otherwise, you won't know where you're going. So, polar coordinates. It's just an alternate way, just like radians is an alternate way of thinking about something as far as an angle. Again, you can have degrees, you can have radians. We can have rectangular coordinates, x and y. That's what we normally do. As a matter of fact, a Cartesian plane is also called a coordinate plane, or it's called a rectangular coordinate plane, because the x and the y coordinates are in respect to the number line, the x-axis number line, and the y-axis number line, rectangular coordinates. Well, we can also have polar coordinates. So let's do an example here, and I'm going to try to keep it simple as best I can. And let's do here I'll use some color. I'm going to do a radius of 10. You know what, I need to go a little bit higher with my angle. And if yours is there, just leave it. I'll just try to be a little bit more accurate here. Radius of 10. Let's form a right triangle. All right, here are the polar coordinates. The first value is the radius. And the second coordinate is the angle. I'm going to go pi over 3. So instead of x and y, it's r theta. So the actual coordinates of the point are given in polar coordinates. Instead of giving an x value and a y value, we're going to give you a radius value and an angle value. Interesting. Just a whole different way of looking at it. And the higher up you get in your trig and the higher up you get in your math, then things tend to go in polar coordinates. And a big part of that is because of S equals R theta is so handy of a formula. It really, the arc length equaling the radius times the angle in radians is really valuable, because in real life, lots of things go in circles. Lots of things. And so that formula comes into play all the time, all the time. So this is polar coordinates, a radius and an angle. And it's not too hard to convert into regular coordinates. Because think about this. The cosine of theta in a Cartesian plane is x over r. Do you agree? Cosine of theta is x over r. Can you solve this for x? That's what I want you to do. I want you to solve that little equation for x. And you're going to solve it in decimal form All right, and I want you to take it to 4 decimal places. Okay, so just solve that little equation for x. Okay, so if you're not there yet, you're just making it too hard because it's really a lot more simplistic. What is the angle? It's pi over 3. X is what we're looking for, and the radius is 10. So it's just a real simple equation. And again, things on the bottom go to the top across the equal sign. So all you're doing is multiplying 10 times the cosine of pi over 3. Now, how can you do pi over 3? You can do it 2 ways. You can put your calculator in radian mode and just punch it out. You put your calculator in radian mode. Or you can convert pi over 3 to degrees. How do you convert pi over 3 to degrees? What do you multiply it by? 180 over pi, right? Because you want the pi's to divide out. So the angle is how many degrees? 60, right? So it's a 60-degree angle. So 10 times the cosine is 60. Anybody got a value for me? 5. 10 times the cosine of 60. Okay. Is it 5 dead on? Oh, yeah, because cosine 60 is a half. All right. Sounds good. Now I'll do the other one. Do the sine of theta equals y over r. And let's figure out the y coordinate. See, we're converting back to rectangular coordinates. We're converting back to rectangular coordinates. So do the exact same thing for the sine, and we'll get the y value. All right, what do you got for y? Jeff, what do you got? Give it to me in decimal. What's the decimal value? Just multiply it out, divide it out. Anybody? Come on. What was the first number? 8.6. All right, and this, so 8.7, right? 1 point round off. So the coordinates of the point are 5 and 8.7 for this situation. Is that a unit circle? No, obviously not, because the radius is 10. So if we were to do this normally, the x coordinate would be 5 and the y coordinate would be 8.7. 5 and 8.7. But if we were going to do it in polar coordinates, it would be the radius of 10 and the angle of pi over 3. But you can see it's real easy to convert from polar coordinates to rectangular coordinates. That's real simplistic. Very, very easy. You're just simply going to use the fact that the cosine is x over r and solve for x, and the sine is y over r and solve for y. That's not hard. What about going backwards the other way? What if they started with an x coordinate of 5 and a y coordinate of 8.7? How could you then take that and go backwards into polar coordinates? So you have an x of 5 and you have a y of 8.7. How can you go back the other way? So what two things do you need to go the other way? You need a what and a what? For polar coordinates and what things? Radius and angle. All right, so those are the two things we need. So how can we get the radius? How can we go back now the other way? Luke? You could use any of the trig functions, although you don't know the angle. So to get the radius, how are you going to get the radius? Do that first and I'll worry about the angle. You worrying about the angle right now? Because I'm asking radius and you're giving me how to get the angle, but maybe you don't realize that. How do you get the radius? All right, so let me see. I'm searching for a clear spot here. So let me just go right here. Look, here's what we've got now. This is the situation. We're like this, and we got a 5, and we got an 8.7 now, right? And we got to go back the other way. And we need this value, this r. How would you find the r? Pythagorean Theorem. Okay, good. You were scaring me for a second, right? Because again, this is the 5 and this is the 8.7. All right, so here, run the Pythagorean Theorem. So you got to do 5 squared plus 8.7 squared. Take the square root and round off. And what do you get? Did you even punch it? No, I wouldn't have either. All right. If all's right with the world, the radius is 10. Because we're going back the other way. Okay, so now we got the radius. So we went from rectangular coordinates. We now have the radius of the polar coordinate. How do we get the angle? How do you get the angle? What ratio? Which ratio are you going to use? Okay, let me help you out. The angle's right here. I heard it. Use the tangent, right? Because you have, whoa, purple. Because you have the opposite and you have the adjacent. So the tangent of theta is going to be the opposite, 8.7, divided by the adjacent, which is 5. Tangent to the -1 button of that. And our angle ends up being 60 degrees. I didn't punch that one either, Alex. Right? 60 degrees. And again, we're a little bit rounded off, so. And then you want radians, so you're going to multiply by pi over 180, right? And you're going to say, oh, pi over 3. So what did we just do? We started out in polar coordinates, and we used the cosine function and the sine function to figure out x and y in rectangular coordinates. And we started out in rectangular coordinates, and we used the Pythagorean theorem and the tangent to get the radius and the angle. It's that simple, but it does come up every once in a blue moon. All right, I'm going to quit there, and you guys got your work to do.